What do you think of when I say the term artificial intelligence? When some people think about artificial intelligence, they imagine a sentient, super intelligent robot wreaking havoc on our society and enslaving us humans to serve their needs. When I think of artificial intelligence specifically in neurophysiology, I imagine a sophisticated tool enabling me to see things that I can't see by just looking at my screen. I imagine a powerful ally that can integrate several systems in the operating room, anesthesia data, vital signs, maybe even imaging data, making surgery safer for my patients. So, there are several questions that we can ask ourselves about the implementation of AI in the field of intraoperative neuromonitoring. What can AI do for the field of neuromonitoring? Where is its development in today's neuromonitoring world? What goals should we expect to achieve using AI in the future? And what is our role as neurophysiologists in developing AI models to achieve our goals? The holy grail of AI and intraoperative neuromonitoring is the development of a model that can take the signals from our neuromonitoring machines, identify when changes are occurring, interpret where the changes are coming from, whether from a technical issue, global physiological changes such as anesthesia, blood pressure, or temperature, or if it's a true change due to surgical manipulation. The AI model should be able to notify the surgeon and the neuromonitoring team. It then should be able to recommend corrective actions to bring the signals back to baseline, thus sparing the patient of post-operative deficits. You might ask, how is AI better than the systems we have now? After all, we currently have well-defined alarm criteria for all of our modalities. Somatosensory evoked potentials have a 50% decrease in amplitude or a 10% increase in latency. Arguably, motor evoked potentials in EMG have a more subjective alarm criteria, but in practice, our current system works pretty well. Well, the issue with these current alarm criteria is that it is reactive. When we see an alarm, we are already behind the curve. The patient is well on their way to injury. The technologist has to act quickly to ensure that the change isn't due to technical factors, anesthesia, or global physiological changes, but is a true change due to surgical manipulation. Overzealous reporting can lead to false positives. Lapses in vigilance can lead to false negatives. Both false positives and false negatives ultimately erode the surgeon's confidence in the efficacy of our monitoring techniques. AI, however, can be trained to be predictive. AI is hypervigilant, never taking its eyes off the screen. AI can be trained to have context, looking for changes that are the most important to prevent post-operative deficits. In this way, the probability of injury can be calculated at every moment during surgery. If the probability of injury increases, it can suggest corrective actions. And because it's continuously calculating the probability of injury, it can suggest corrections even before our traditional alarm criteria have been reached. And AI models can be trained to do this over all modalities simultaneously, taking into consideration the interaction of these different modalities and how their changes individually and in concert paint a clinical picture. Different artificial intelligence algorithms could be used to identify important features of our waveforms that we cannot see or comprehend in the time domain. Take, for example, motor evoked potentials recorded from distal muscles. Perhaps amplitude or latency may be shown to be important indicators of change in our AI model. But we know in the presence of anesthetic agents, especially when TIVA isn't offered, We often cannot see these changes until the waveform has disappeared. Perhaps something else in the way the motor evoked potential waveforms behave is important. Perhaps what's important is in the frequency domain, and fast Fourier transform can be used to produce a graph of the frequency spectrum. Perhaps it's in the time frequency domain where the frequency spectrum changes over time. Perhaps it's in the statistical complexity domain where entropy can be used to see changes in the complexity of the waveforms. The point here is, we don't know what algorithms might better classify changes in each of our modalities because the research hasn't been done. Of course, this provides an exciting new branch of research in intraoperative neuromonitoring and an opportunity for us as neurophysiologists to expand the efficacy of monitoring. I'm sure that the practical use of these different algorithms is foreign to most of us. I know it is to me. I can read papers, understand the concepts, but I'm at a loss when it comes to doing the math. This is the realm of the data scientist. So in order to perform research in this area, we either have to become more familiar with these data science concepts, encourage more data scientists to enter the neurophysiology discipline, or at the least collaborate with the data science community. Data scientists are great at knowing what different algorithms can do and how to program them to do it. But they lack one thing we as neurophysiologists have. We have context as to what is clinically significant. We have a better understanding than the data scientists of what we need in an intraoperative neuromonitoring AI model. Therefore, we as neurophysiologists must be the gatekeepers to ensure that as AI models are developed, they have context and the ability to identify clinically significant events. Take, for example, this 2025 paper by Parduzzi et al. They developed an AI model that could classify random motor evoked potential waveforms and tell which muscles they were recorded from. The premise of this paper was that mislabeling MEP waveforms is an issue that needs addressing. They were able to satisfactorily train an AI model, and that model could reasonably predict whether recorded motor evoked potential waveforms were from proximal or distal arm muscles or proximal or distal leg muscles. This is a great feat that demonstrates that an AI model could be trained to classify motor evoked potentials. However, I am rarely confused by the placement of recording needles and the setup of my recording montage. I would have liked to have seen this AI model do something else. I would have liked to have seen the AI model identify changes in MEP waveforms over time. Perhaps this is in their future research plans, but as a neurophysiologist, I have context as to what is clinically important to me in my practice. My belief is that the rate-limiting step in developing an intraoperative neuromonitoring AI model is the lack of available data sets for training and validation of AI models. AI models in EEG don't have this issue. This is mainly because of the explosion of research done in brain-computer interfaces, where data from EEG waveforms, either raw or evoked activity such as contingent negative variation or P300, is used to control assistive devices that help people with disabilities have a more productive life. If you look at GitHub, there are over 60 open-source EEG datasets in their repositories. In addition to these open-source models, there are several commercially available EEG datasets. We don't have these in intraoperative neuromonitoring. Therefore, to be able to develop neuromonitoring AI models, we should have our own datasets of both normal and abnormal waveforms. These should come from different sources, either institutional or through private neuromonitoring providers, since we all have a slightly different way of doing things. We as neurophysiologists should be leading this development since we have the data and we know the context of how AI models should be developed to meet our clinical needs. Presently, research in AI with regard to intraoperative neuromonitoring is in its infancy. Few papers describe working AI models dealing with intraoperative neuromonitoring. Many of the recent papers describe hypothetical AI models and outline flowcharts of how they should work. As far as I can tell, there's only one commercially developed AI model used for intraoperative neuromonitoring. This is the Nervio AIM. From my understanding, the device is in clinical trials in the US. It's a standalone intraoperative neuromonitoring co-pilot. It interfaces between existing neuromonitoring machines, the monitoring team, and the surgeon. It gives a clear picture as to changes occurring and offers solutions to correct these changes. I am positive as their research continues, this device and other devices that will certainly follow will be a powerful adjunct to the neuromonitoring team, hyper-vigilant, detecting changes in ways that we cannot currently do, and providing clear feedback to the surgeon. Will these AI devices make the technologist and neurophysiologist obsolete? I highly doubt it. Over the last several decades, we have seen the rise of autonomous monitoring machines. These have had little effect on our practices. However, we as neurophysiologists should be involved in the development of these AI devices to ensure that they are trained properly and that we have the ability to intervene in their decision-making processes. In this way, these devices can be a useful tool in our ability to ensure patient safety during surgery. So let's play a thought game and develop a flow chart for a hypothetical intraoperative neuromonitoring AI system. This is a fun exercise, and it points out some of the challenges in developing such a system. This section is loosely based on a 2023 paper by Wilson and all out of LSU. First, since this will be a commercially available system, let's maximize the user experience, known as UE in programming jargon, by coming up with a catchy name. Let's call it IONM Bot 3000. Let's give it a cute icon. So here's an outline of what I think an AI model workflow should look like. Let's go through it piece by piece. First, we take our raw data, our waveforms, and we pre-process this data so that the AI model is only looking at relevant information and minimizes noise. So in this block, we do things like analog and digital filtering. We can clip out unnecessary parts of our waveforms. We can do things like principal component analysis or independent component analysis to narrow down what the AI model is given to process. Then we pass this data on to the first real algorithms of our model. This is feature extraction. Here, algorithms could be applied to look at the data in one or more domains, whether that is in the time domain, frequency domain, statistical complexity domain, or whatever we determine through basic research is the most important feature of each modality. We can use neural networks such as a convolution neural network or temporal convolution network to transform this waveform data and classify them for the next step in the process. Concurrently with waveform data, we would feed external data to the model. Things such as anesthesia and vital signs. These could be imported directly from the anesthesia machine through APIs, which allow different software systems to talk to each other, or they could be entered manually by the technologist. In addition, the technologist could enter any relevant troubleshooting data or other observations important to the case. Next comes the heavy hitters, the detection algorithms. Using things like recurrent neural networks and long short-term memory, each current waveform or epoch could be compared to a baseline. This would allow changes to be recognized and trended over time. Information from our external data box would be added to give context to these changes. Next comes interpretation. This is where large language models shine. The LLM can integrate the detection algorithm data and knowledge from a vector database that contains the clinical knowledge of what these changes mean. Relevant observations could be entered from the neuromonitoring team. Then the LLM could reason in real time and determine if a change in waveform is significant and what interventions will likely correct the change. Then the change can be communicated to the surgeon, ideally on a graphical interface showing the alarm, the area on the patient where the change is occurring, and can suggest corrective action to bring the alarm back to baseline. Easy, right? Well, not so fast. Development of this device has issues that must be overcome. First, and probably most importantly, basic research has to be done to discover which algorithms could give us the best way of identifying significant changes in each modality. Like I said earlier, this is an exciting new research area that is opening up in neuromonitoring. Secondly, in order to do this research, we have to develop large data sets of normal and abnormal intraoperative neuromonitoring data across all modalities and across multiple centers. This is a big task, but we generate the data and we should control its use. Next, the accuracy and efficacy of the model has to be proven over hundreds or thousands of validation and real-world cases. The output of the AI model must be compared to human scoring of intraoperative neuromonitoring data. If and only if the AI model is as good or better than human scoring, can it be trusted to work independently? I think it's imperative that even with a working AI model, the reading neurophysiologist must be able to override the decisions of the model if they do not agree with the suggestions given to the surgeon. The next challenge comes from the very nature of large language models. Large language models, as they exist now, are very prone to confidently giving out bad advice. This is known as hallucinations. You have to realize that LLMs are trained by scraping the internet for information. However, the quality of this information is imperfect. They are scraping data from portions of the internet that are free for them to use. So, as you can imagine, much of their information comes from sources such as Reddit or Wikipedia. They are not being trained on Journal of Neurosurgery, Spine, or Journal of Neurophysiology. Thus, they don't have access to the same knowledge base that we as neurophysiologists have. And their knowledge base has a cutoff point. It only extends to the date that the LLM was trained. For example, the latest version of ChatGPT, GPT-4o, was trained in April 2024. So any knowledge or techniques developed after this date isn't in its knowledge base. The way around this lack of expertise by the LLM is the use of a RAG vector database. RAG stands for Retrieval Augmented Generation. RAG is a technique that allows the LLM to search for current information stored in a database created for a specific topic or specialty. So, for example, if we as neurophysiologists created a RAG database that was a compendium of all of our current scientific and clinical experience, the LLM could pull from this database and be up to date on the most current clinical knowledge. Thus, it could be as smart as the smartest reader in the room. But the database must be continually updated with the latest knowledge as time goes on. There are also different ways of chunking data and weighing data when putting into the database to ensure that the LLM gets it right. This is a finessed art. A bad database is actually dangerous as it might allow the LLM to confidently give bad advice to the reader and the surgeon. Lastly, there is the issue of trust. Do we as humans trust AI? Have you ever taken a Waymo cab? Isn't it disconcerting that you get into a car and there is no driver? How much do you trust it to get you to where you're going safely? In your mind, you know it's been programmed to drive accurately, avoiding obstacles and other cars. But in the back of your mind, aren't you just a bit unnerved that there is no human to control it in case something goes wrong? Any AI model used in intraoperative neuromonitoring will have to prove its accuracy and efficacy, and it will take time for us humans to trust its advice. So there you have it. AI is coming to intraoperative neuromonitoring. It's up to us as neurophysiologists to be the gatekeepers to ensure it meets our needs. Will AI be a friendly co-pilot, or will it be an evil robot overlord? The future is in our hands. To finish, I would like to recognize the members of the Asset Innovation Committee who are instrumental in getting information about AI, BCI, and other technical innovations into the hands of the intraoperative neuromonitoring community. Thank you.